Hello, this is Group 42. This is Gareth Fuller, Fabian Uribe, and Carlos Zamora. We're talking about nuclear fuel reprocessing today. So our process is reprocessing used fuel from light water reactors into fuel for fast breeder reactors. The waste is stored for hundreds of years and need only be stored for hundreds of years instead of hundreds of thousands or tens of thousands. It's a relatively close fuel cycle as it cycles the bulk of the material through again and again with only pulling out small amounts of waste and needing a small amount of addition of uranium here and there. The chemical reaction. For the first part is the pyrochemical reduction of light water reactor metal oxides using lithium in a lithium chloride bath. The second part is the electrorefining or pyroprocessing of the now metallic light water reactor waste and the used fast breeder reactor waste. In this cell, the uranium, plutonium, and actinides are oxidized and moved to a liquid cadmium pool. Once they're reduced in the cadmium pool, uranium and a mixture of uranium, plutonium, and actinides move to iron and cadmium cathodes, respectively. After separation, the desired metal is able to be removed and melted into fuel rods, which are then reintroduced as fresh fuel into the fast breeder reactor.
The first step of this process requires the fuel to be compatible with the second step, and to do this, it has to undergo oxide reduction. The uranium, plutonium, and actinides are reduced to metal, then washed with lithium chloride and put into an electrorefiner, and the remaining fission products are left in a salt bath. Pyroprocessing is carried out in a cell containing chloride salt floating on liquid cadmium. An anode and cathode are used to help transport the uranium and plutonium, and the actinides stay with them throughout the process. Materials are then recycled into new fuel, eventually destroying the actinides via fission. Overall, the process reduces waste and shrinks the time needed to allow the waste to become no more radioactive than uranium ore. Regarding demand, it provides energy from used fuel to other reactors. Currently, there's about 80,000 metric tons with an additional 2,000 per year. It also is a clean energy source, so it has no pollutants released into the atmosphere. It is also has a smaller land footprint, provides more energy than fossil fuels, and is proliferation resistant because the plutonium isn't separated out.
In terms of scaling up, there's plenty of nuclear waste available from light water reactors. So there's a huge untapped amount of reactants present that are able to be used. And then the political environment is becoming increasingly favorable for implementation of alternative fuels as fossil fuels are phased out. And nuclear will be important among them because it is very stable. Unlike wind and solar energies, it does not rely on external conditions such as the sun or wind, but it can operate independent of those. In terms of enhancing sustainability, the closed loop salvages light water reactor waste and reuses fast breeder reactor fuel, which means there's less final waste to store. And this means that there's less storage time and reduced toxicity because the large high half-life isotopes are burned in the reactor once they're passed through multiple times. And this allows for geologic disposal because in a matter of 300 years, the final waste, can be reduced to the same radioactivity as uranium ore, and this allows for geologic disposal. And above all else, it generates clean power.